C'est juste pour vérifier que... Attends.
On me voit là ou pas? Ok. Alors, bonjour tout le monde. J'ai commencé en français d'abord. Donc j'ai été, après une pure réflexion, on m'a désigné comme président de ce jury, donc de la thèse de Alice, Jaccod, et je vais vous présenter les membres du jury. Donc je vais commencer par moi.
Ça va?
Président, je peux commencer par moi. Je suis Maurice Rossi, donc directeur de recherche au CNRS, ici même à l'Institut anglo-saxon. On va passer Stéphane. Oui, tiens.
Bonjour, donc Stéphane Pepinet, moi je suis directeur de recherche à l'Institut d'Alembert et je suis invité dans ce jury.
Ouais. Donc, bonjour, donc François Schmitt, directeur de recherche au CNRS également. Je suis membre du laboratoire d'océanologie et de géosciences qui se trouve à Wimereux, au nord de la France. Et je suis donc examinateur.
En français. Bonjour, Alessandra Lanotte, je suis rapporteuse de cette thèse. Je viens de l'Italie, du sud de Lecce. Je travaille dans l'Institut de nanotechnologie.
Et bonjour, Enrico Calzavarini, maître de conférence à l'Université de Lille, et je suis invité dans ce comité.
Bonjour à toutes et à tous, moi je suis Sergio Kibbaro et je suis un des directeurs de thèse, nombreux directeurs de thèse de Alice. Je suis professeur à Paris-Saclay-Mat.
Si les gens qui sont en ligne peut-être peuvent se présenter ou je les présente. Est-ce que vous m'entendez? Can you hear me?
Cristobal. I have to introduce myself. Sorry. My name is Cristobal López. I'm professor at the University of the Balearic Islands in Spain. Good morning, everybody.
Can you hear me?
Bonjour à tous. Stefano Berti, maître de conférence à l'Université de Lille et je suis un co-encadrant de l'ICE.
So, Cristobal, could you introduce yourself?
Il ne s'aime pas.
Okay, maybe I will introduce it. Can you hear me, Cristobal?
Non.
Okay.
Non, il y a un problème.
Okay, so I will introduce Cristobal Lopez, he's professor.
Yes.
Okay.
Sorry, the music is too loud.
Yeah, okay.
Which music?
Can you introduce yourself?
What music? Why do you hear the music?
Well, maybe I will introduce Cristobal. So Cristobal Lopez is professor at Palma de Mallorca in Spain, and he was the second referee of Alice's thesis. Okay, so maybe we'll start now.
But can you hear me, Cristobal?
Yes, I can hear you, but I cannot hear the other person speaking. I can hear you very well.
That's
Okay.
right. Okay, so we will start.
Non, attends. Ouais, oui, mais il faut... Allez. Ok. Yes. Okay, thank you. So, good morning to everyone. Thank you for being here. Today I'm going to present my PhD thesis, which has been done here at the Institut d'Alembert under the supervision of Sergio Kibbaro and Stefano Berti. The title is Direct Numerical Simulation of Complex Multiscale Flows. Turbulent multiscale flows are ubiquitous in nature and can be observed on a wide range of scales, ranging from large-scale flows like ocean and atmosphere circulation to small scales one, like, for example, the smoke from a cigarette. Besides the different physical contexts where you can encounter turbulent motion, there are some common features that can be listed. Turbulent motion are unsteady, regular and chaotic, and are really characterized by several scales, both in terms of space and time. It's really important to face the study of turbulent flow, basically because the majority of flow that you can encounter in physics and also in engineering application are turbulent or become turbulent at some point. Even in the solar line, the trace of a cascade of turbulence has been evidenced. And secondly, because of the effectiveness of turbulence in terms of mixing and diffusion of matter, momentum, and heat with respect to the laminar flows. Across the years, several methods, several tools have been developed to study turbulence as a phenomenon in its several applications, and with the theoretical and experimental investigation of turbulent flows, nowadays, thanks to the high-performing computer resources, we can tackle the problem from a numerical point of view. There exist three main classes of numerical simulation of turbulence, starting with the Reynolds average Navier-Stokes simulation, going through the larger simulations for arriving to the direct numerical simulation. There is a clear compromise in terms of accuracy but also computational cost. In this case, we really focus on the last numerical tool, which is the direct numerical simulation. To give you an idea of the complexity of the problem, if you want to solve all the scales of your flow, so going from the large length scale to the smallest one, you need to have a number of grid points which is proportional to the Reynolds number elevated to 9/4. So, generally in physics, the Reynolds number is really high. Here, just to give you an idea of the typical value of Reynolds number in the ocean or in a tropic in the atmosphere. So clearly, it's highly computational costly. In these cases, then, we decided to study turbulence from with different approach. For starting, we look at the classical configuration of turbulence, which is homogeneous isotropic turbulence, for studying a statistical mathematical problem, which is connected to a version of the Navier-Stokes equation. Then we pass to a study of a more complex situation in terms of a non-homogeneous turbulence coupled to the reactive Planck dynamics. Also, in particular, by focusing on ideal situation, the idealization of these predator-prey Planck dynamics in the way behind an obstacle. And therefore, we face this problem both in a two-dimensional and three-dimensional configuration. Aside as I also collaborated in a work about another type of turbulence, which is the one induced by body agitation, but today there is no time to show you these results. So, as I said, the first part is about homogeneous isotropic turbulence from a statistical point of view. A fully developed turbulent flow is a phenomenon which is highly dissipative and far from equilibrium and irreversible, in the sense that if you try to apply the temporal inversion operator to the equation of motion, meaning that you want to invert the error of time and also the sign of velocity, the Navier-Stokes equations are not symmetric under this operator. And this is because of the presence of the viscosity coefficient, which tends to phenomenologically describe the disorder at molecular level. So one should ask what happens in the limit that this coefficient tends to zero, equivalently to the in the limit of the Reynolds number, which tends to infinity. And we know that the signature of reversibility is conserved through the appearance of the dissipative anomaly in three-dimensional turbulence, which means that the mean kinetic energy dissipation remains constant in this limit. So clearly the study of turbulence and of this particular singular limit is quite complex because of its asymptotic nature. An alternative approach has been proposed by Galavotti through the equivalence of dynamical ensemble conjecture. His idea, in fact, is to propose an equivalent version of the Navier-Stokes equation, which are formally time-reversible. This means that at the place of the constant viscosity, you can put a fluctuating viscosity term, which acts as a thermostat for conserving a general quantity like energy or entropy. So the focus of the conjecture is really on studying this singular limit, and so the implication of this singular limit, and on proposing in some sense a statistically equivalent description of fully developed turbulence. One of the principal aims is to pave the way for creating a link between the turbulence as phenomenon and the general framework for non-equilibrium problems in statistical mechanics. So, in mathematical terms, we consider an incompressible flow with a forcing acting at large scales, and we solve the Navier-Stokes equation, the standard Navier-Stokes equation, and the reversible version of it, where the coefficient alpha can have two different expressions depending on the quantity that you want to conserve in your system. So, in mathematical terms, the equivalence says that in the limit of high Reynolds number, of large Reynolds number, the system is mainly chaotic, and so the fluctuating viscosity is subjected to a sort of homogenization phenomenon, which implies that a large class of local observables can be described in the same way by the two ensembles, the one defined by the constant value of the viscosity, and the second one defined by the global value of the quantity, which could be energy or entropy, or for other choices. So we can trace an analogous of this equivalence in terms of the equivalence of ensembles in equilibrium statistical mechanics in the thermodynamic limit which exist, and it's true, between the canonical ensemble and the microcanonical one. So we test the validity of the conjecture both for a two-dimensional turbulence, but mainly we focus on the three-dimensional configuration because before now the equivalence was not demonstrated yet. So we look at a cubic domain with periodic boundary condition with a Taylor-Green forcing acting at large scale. And the numerical procedure was to perform a standard Navier-Stokes run until the system reaches a stationary state. Then we initiated the reversible Navier-Stokes run from the last velocity field, and eventually we changed the viscosity coefficient to explore a certain range of the dependence on the Reynolds number. All our simulations were resolved in the sense that we resolved all the scales until the dissipation scale. Here I show only the results for the three-dimensional case, which is more interesting, and we looked at the three different values of the Reynolds number, and in our simulation we decided to take the astrophy constant because it's more interesting in terms of the singular limit. In fact, if you look at the first graph here, you can appreciate the temporal behavior of the kinetic energy dissipation, which in the Navier-Stokes run fluctuate because of the fluctuation of the entropy, while in the reversible Navier-Stokes run, the fluctuation are due to the viscosity coefficient, which is now not constant. In the case of the highest Reynolds number, it widely fluctuates around the mean value. In the right-hand graph, we verify that the conjecture, so the fact that the mean value of the fluctuating viscosity should tend to the constant value of the viscosity coefficient, which is true within the statistical error for all the Reynolds number here explored. The stringent test of the conjecture proposes the equivalence of local observables, but we push further the investigation of the equivalence by looking at some statistical observables which are crucial for turbulence, like the energy spectrum, which turns out to be indistinguishable in the two models for all the Reynolds number. And more interestingly, we look at the scale-by-scale flux of energy by applying a filter to the velocity field to looking for how the energy is transferred scale by scale, and the mechanism of turbulence is really the same in both models. Moreover, we studied at the behavior in the two models of another important observable, which are the structure functions, by extrapolating the typical exponent, which turned out to be equivalent in two models and in accordance with the turbulent shell model. This is an important result because it shows the fact that the intermittency is really a property of the inertial scale range. The stringent test of the conjecture is really about the fact that the mean value of the viscosity should tend to the value of nu. But it's interesting also to look at the PDF, so at the fluctuation of this quantity, and we see that in the case of a highly chaotic flow, so at the highest Reynolds number, the PDF is quite flatter and some negative, rarely events are recorded. To conclude, we have also performed another test to ask to ask ourselves a question: is it the reversible Navier-Stokes equation capable of generating a turbulent velocity field not generated by genuine Navier-Stokes dynamics? For answering this question, we repeated the reversible Navier-Stokes simulation at a certain Reynolds number, but starting from the Taylor-Green velocity field with a certain amplitude of the velocity such that the total entropy of the system at the initial time is equal to the mean value in the Navier-Stokes equation. And the results show that the reversible Navier-Stokes is able to generate a correct dynamics from generic initial condition. So to conclude, to draw some conclusion of this first part, we verify the validity in a fully developed turbulent flow in presence of a cascade of energy, that the conjecture is correct. And we push further the verification of this conjecture by observing all the relevant statistical observables, which are really equivalent in the two models. And the important result is the fact that at the end the turbulence is unaffected by the presence mechanism of dissipation. And in this sense, for a perspective, it should be noted that reversible eddy viscosity models have been already proposed and studied in the framework of large eddy simulations. From a statistical point of view, the interesting point of this equivalence is the fact that the turbulent fluids could be considered in practice as reversible. And this means that non-equilibrium statistical mechanics, like, for example, fluctuation relations, should apply. So, in the second part of the thesis, as I said, we looked at the case of non-homogeneous turbulence in the presence of a predator-prey plankton dynamics, where plankton is. If you look at the sea surface, you see the green chlorophyll, which is contained in phytoplankton, which changes affected the color of ocean, and it's also visible from the satellite, where these wonderful structures are visible. With the term plankton, we intend a large class of a huge variety of organisms, both from marine and freshwater environments, which have a limited capability of swimming, but predominantly are drifted passively by the current. Within the large variety in terms of sizes and characteristics, here I put an illustration of two species of phytoplankton and zooplankton. Why is it so important to study the plankton dynamics? Because they constitute the 90% of marine life, and in particular the phytoplankton, because of this its role in the photosynthesis, it's really important for the entire aquatic food web and global ocean and global production of oxygen. The range of scale is really wide because you can find species of plankton above the micron, below the micron, arriving to the biggest species, which are the zooplankton or the one of the dinoflagellates. It's interesting that the chlorophyll distribution in the ocean surface is not shows a clear relationship between flow structures like eddies and fronts and the plankton distribution, and thus it's clear that it's mandatory to study the problem of plankton dynamics in connection with the fluid environment. Among the variety of physical and biological interaction which control plankton blooms or their typical patchiness, a prominent role is played by fluid transport. And this problem has been investigated in terms of linking the mechanism of emergence of algal blooms with current structures like eddies and filament through kinematic flow model coupled to effective biological models. This has been the starting point of our work because we decided to take a more idealized approach to test the robustness of the mechanism of appearance of this non-trivial interplay between the transient character of the flu and a type of reactive dynamics. The first ingredient you need to study the plankton evolution is the biological model. Generally, it's a really complicated task, and it exists several models which are based on coupled nonlinear differential equations. Two main approaches can be recognized. There exist the realistic models, which are really includes several parameters and species, while it exists a second class of idealized models, which includes 2 or 3 ordinary differential equations, which with the aim of capturing the qualitative behavior of and to disentangle some key mechanism. Across this model, for example, there is the PZ model, which is the most idealized situation where you have only a predator-prey plankton interaction between the phytoplankton and the zooplankton, which gives the name to the model. By looking at the phase space, you can see that you have the U variable, which represents the phytoplankton, which evolves on a faster time scale, while the other variable is the zooplankton. If you perturb the system starting from the point 1, which is the equilibrium of the two species, the coexistence of these two species, for a small perturbation, the system suddenly comes back to the equilibrium. But if you perturb the system above a certain threshold, it can follow a long trajectory in the phase space, being excited and then coming back to the equilibrium value. So to complete the framework of the evolution of population densities, you need the biological model and the advection and an equation for the advection and diffusion, which is here highlighted. Without entering the details, just to say that the model, the PZ model, so the biological part of the equation, could display different behaviors depending on the parameters that you adopted. But for the range of realistic parameters that we adopted in our simulation, it has only a stable equilibrium point, but can display excitability. The flow is really an idealized configuration that we choose to look at. So we have the typical Navier-Stokes equation with the parameter, the Reynolds number, which is based on the typical size of the obstacle. So this is a sketch of our computational domain. We have only an obstacle which mimics an idealized island, and the flow encounters this obstacle, and the vortices are shaded. The flow is really open flow in the sense that the trajectory continuously leaves the domain. The other important parameter in our simulation is the Schmidt number, which accounts for the effective diffusivity of swimming algae. Sorry. Our simulation have been performed by using the code Basilisk, which has been really efficient by adopting an adaptive mesh refinement in order to resolve all the scales of the problem and to explore a wide range of Reynolds number, going from the periodic case arriving to a highly chaotic situation. So, in the absence of advection, we firstly studied the behavior of the system. So, the biological model, as anticipated, can display excitability in the sense that an algal bloom can appear if you perturb the phytoplankton above a certain threshold. Then the two species comes back to the equilibrium because the excitability is only a transient phenomenon. When you let the two species evolve in a fluid environment by, for example, localizing a patch of phytoplankton density entering the system, the picture changes. In the sense that we see the emergence of a permanent excitation of the predator-prey system with a typical time behavior which is dictated by the vortex shading, and there is a clear correlation in terms of spatial distribution of the species and the typical flow structures, so vortices and filaments. The key mechanisms which have been studied are the straining action exerted by the flow, which contrasts the reaction diffusion spreadings, and moreover the existence of a stagnation point upstream and downstream of the obstacle, where the two species are trapped for a while. Also, the open boundaries are important to avoid the homogenization of the density, of the scalar densities. So, as we found the results which are in accordance with this model, this configuration studied with kinematic flow model, in the sense that the two species start to oscillate around a certain value, which is not the equilibrium, with the typical period given by the flow. Another crucial parameter, aside from of the period, is the ratio of the transport time scale to the biological activity once. And this is, we varied this parameter in the equation to investigate the impact. For example, by looking at the primary productivity, which is the linear growth term in the phytoplankton equation, we found that an optimal value exists of this parameter epsilon, which means that the flow transport is lower than biological growth. The two opposing limits, in some sense, have the effect of hampering primary productivity. Our idea was, in fact, to investigate this mechanism of emergence of algal bloom in a dynamic turbulent flow. And for doing that, we looked at the impact of the Reynolds number. And what we found is that if the fine scale details really changes are affected by the increased chaoticity of the flow, the general behavior of the system is really unaffected by this parameter. We computed the spectra of velocity and scalars, and we found that we are in presence of a direct entropy cascade for the velocity, while the scalar fluctuation spectra show a tendency, typical scaling of a passive non-reactive scalar. But this prediction, so scaling according to -1, is also in accordance to the theoretical prediction of two interacting species according to a Lockta-Volterra predator model. It's really important, which is another important result of our work, is the fact that it's interesting that the fine scale, so the small scale of the problem of the fluid, only impact the fine details of the scalar statistics. So it's useful to look at the impact of performing some under-resolved simulation. For example, we look at the case at the highest Reynolds number, and we repeated the simulation with a slightly under-resolved simulation, and a third one which is more under-resolved. And the results are that while the second simulation is really efficient in capturing the results and the dynamics as in a fully developed, in the fully resolved simulation, the third case introduces consistent qualitative and quantitative errors in the flow and in the scalar dynamics. Finally, we look at the possible impact of the roughness of the obstacle, because a real island should be clearly not smooth but characterized by fractal structures. And we repeated the simulation with the fractal contour shape of the obstacle, but the results, both in terms of the qualitative and quantitative behavior, is weakly dependent on the details of the boundary layer. So to conclude the second part, we found that in accordance with kinematic flow models, it exists a persistent condition of a persistent excitation of a plankton system due to the coupling between the advention by an open flow and biological dynamics which displays excitability. The key mechanisms are both the existence of a stagnation point where the species are trapped, and the ratio between the biological time scales and the flow time scales. The important fact is that we studied the dependence of the results on the Reynolds number, and we see that these only affect the statistical properties associated with fine scales, and this paves the way for assessing the validity of a coarse graining approach, even in this configuration. In the last part of this thesis, we look at the possible effect of a three-dimensional turbulence on this particular type of plankton dynamics, and with the aim of unveiling possible differences or similarities, and so to test also the robustness of our results. And this should be considered as a first step for more realistic configuration with respect to the idealized approach we took. Here, so we mimic, we can appreciate the behavior of the phytoplankton field behind the cylinder, which is trapped in the flow structures over all the height of the cylinder. The equation that we solved are really the one introduced in the previous part. And for the third dimension, we put periodic boundary condition. And we decide to look at an intermediate value of the Reynolds number because of the increased computational cost, as well for the Schmidt number. To make a consistent comparison with the two-dimensional results, we repeated the two-dimensional simulation with the same parameters. By looking at the flow wakes, we see that deep differences exist in terms of the vorticity field in the three-dimensional case with respect to the two-dimensional one, meaning that in the sense that the typical coherent structures are here absent because the head is a stretch along their normal direction. So this is the first sign of the fact that the underlying carrying velocity field is quite different, as is also highlighted by looking at the different behavior, for example, of the kinetic energy of the flow. Besides this difference, the response of the plankton species to this situation is that by introducing the same perturbation, in this case on O at each plane Z, the response of the system is really equivalent in the three-dimensional and the two-dimensional case, in the sense that an excitation exists, which is permanent, with a slightly difference that now the behavior is not perfectly periodic, and that the total content of phytoplankton in a 3D case is slightly below the two-dimensional counterpart. In this case, we can argue that the persistence of excitation depends on the relation between the typical time scale of strain and to be intermediate between the two species biological ones. By looking at the spatial distribution of the phytoplankton, we see that the image is slightly different from the two-dimensional case, in the sense that it's not possible to recognize localized structures in terms of vortices and filaments, and this reflects the much more better mixed nature of the 3D flow wake. We analyzed the spectra of both velocity and scalar fluctuation to assess for better understanding the patchiness, for example, of phytoplankton and zooplankton. And for the energy, we see the presence of a direct cascade of energy, while, as expected in the three-dimensional flow, while for the two scalars, our results, which are the colored curves, show that in this case, the typical scaling is the one expected for a passive non-reactive scalar. So according to kappa elevated at minus 5 over 3. There is a slightly less steeper spectrum for the phytoplankton component at larger scale, which should be the signature of the biological nature, the biological interaction, which at this scale are more important. So to conclude this second part, we saw that beside the important difference in terms of the nature of the flow, the qualitative behavior for this particular excitable model of phytoplankton and zooplankton is really equivalent in the two cases. And in terms of the mechanism of permanence of the excitation, which is due to the ratio between the time scale or large scale strain rate and the phytoplankton and zooplankton reproduction. And the fact is that also in this case the spectral analysis suggests that planktonic species behave as passive non-reactive scalars. The main difference of the three-dimensional dynamics we can say is that in terms of an hampering of the primary productivity, because of the fact that the wake in the three-dimensional case is quite more different with respect to the two-dimensional one in terms of the absence of typical structures like vortices and filaments. So to draw some general conclusion of this thesis, we have studied the problem of turbulence by adopting a direct numerical simulation approach with the Basilisk code. And while in the first part of the thesis, we studied the more fundamental, this turbulence from a more fundamental point of view, we can say that we perform a Gedanken experiment, and so it's the only possibility here is to use the direct numerical simulation, and we show, because it's important to resolve really all the scales of the problem, and we can say that we solved this problem in this context by showing that the conjecture equivalence of dynamical ensembles is correct. In the second part of the thesis, so about the plankton dynamic, we look at a different type of turbulence, which is non-homogeneous turbulence in the wake behind an obstacle, and coupled to a non-reactive dynamics, and we see that the role of small scales is not really prominent in terms of plankton dynamics, and so which is more influenced by the large scale flow properties. And this is an important result because it assesses the possibility of use a more coarse-grained approach, which is really useful for studying more realistic configuration, for example in geophysical context where the spatiotemporal scales range is really wide, and so a DNS approach is unfeasible. In this according to these results, the future perspective of this work are really about the second part of the thesis. So our idea in the future is to study more complex models of biological interaction, for example by including the important role of vertical upwelling of nutrients, for example by adopting an NPZ model. And secondly, our idea is to investigate a more realistic three-dimensional flow configuration by including the effect of stratification, rotation, and temperature. And a possible way to do that is by employing the multi-layer model, the free surface multi-layer model proposed in Basilisk. Another test bed for this efficient computational method is by looking at the impact of the sub-mesoscale flows for the plankton dynamics. Thank you for your attention.